In this video, I will review this orthogonal trajectory problems in differential equation, and mainly in this video we'll try to relate these two things, orthogonal trajectory problems and integrating factor problem of the differential equation in differential forms. So typical orthogonal trajectory problem is introduced as follows. First, we look at two variable function on the left-hand side. And as we vary the right-hand side, which is a constant, for example, if you put c equals 0, that'll define one of this curve in white. If I change that value to something else, then it'll give you a different curve, and to something else, it'll give you different curves. As we vary this c, we have these different types of a family. Because they all give a different value, these functions will never intersect each other. Also, these are known as a level curves of the two variable functions. So this is one way to define family of a curve, varying the one of the constants that is involved in here. You may be theoretically or practically, you can isolate this value c. The problem is that if we have this family of the c, can there exist a curve like this blue one here, so that if you put it down here, this blue curve, a single curve here, is happen to be orthogonal to all the curves that is listed in here, in a sense that their tangent line at each intersection point there is perpendicular to each other. So if you can find one like this, can we find another one that starts at different points? Because it starts at this point, maybe you should start at a different point and ask the same question. So this is typical orthogonal families. This blue family is always intersecting any member of this white family over there. It seems like we're able to kind of sketch this one given the family, and so often we don't ask that question whether it exists or not, but it is actually the big question. If I write down this family of curve, is it always is there another family of curve that always perpendicular and intersect given family? So this existence is one question. So testing orthogonality is not usually done through tangent lines, but it's actually done through normal line, which is the line that is perpendicular to a given curve instead of tangent line. But if you compare the two normal lines, their perpendicularity must be preserved as well. So for example, if you look at the white line here, that one is the tangent line, but instead of the tangent line, we look at this normal line to the white line. And if you look at this blue one, instead of looking at the tangent line there, we look at its normal line. But if the two tangent line of these two things are perpendicular to each other, their normal line to be perpendicular as well, because it's kind of rigid motion of this tangent line. So we detect the perpendicularity of this tangent line by the perpendicularity of this normal line, which is calculated via this gradient vector field. So let us review a little bit about the gradient vector field. This is a typical context. We have two variable functions, set it to 0 or constant. Then it'll define a curve. And there's something called implicit function theorem. We can assume if it satisfies conditions such as continuous partials and stuff, then we can assume there is a nice parameterization. So if we have this curve and we have this parameterization, so using that parameterization, we can form this position vector field. This is position, relative position, relative to the origin. And it's a formal derivative, x prime and y prime, supposed to give you the velocity vector. As sketched here, this is a vector that is perpendicular to this velocity vector, which is this notion in here. And that normal vector is denoted by this delta upside down notation, nebula, I think it reads. We call the gradient of f. And we'd like to review this where this gradient rises. And this equation is a functional equation. F was originally a two-variable function. Now with this composition, is now one variable function. And what happened with this composition of one variable function, it becomes this left-hand side as a function becomes a constant function. So there's one variable function. After you went through this function, they all cancel out, become zero function. So its derivative makes sense in terms of t with respect to t, and right-hand side is a constant function differentiated with respect to t. So that gives this formula. This formula is called a chain rule. The chain rule is the one that is responsible to tie this normal vector, perpendicular vector, to the velocity vector, to these partials of f and partials of y. So left-hand side by chain rule, it looks like this, and there's multiplied by the x prime and y prime, which is a component of velocity vector right there. So we can rewrite this one. It's a dot product of two vectors. So this component, partial x and partial y, and collected together here, and this x prime and y prime are collected here, and this forms a dot product equals 0. That's the perpendicularity. And it happened that first partials of f are actually one of the vector that is perpendicular to the velocity vector, hence it can serve as a normal vector. So this one is denoted by this gradient f. X component of partial x, y component partial y. So let me remind you of our original problem. Now we just reviewed these orthogonal trajectories, and our goal is tying this one to integrating factors of differential forms. So here is a formulation. To ck is actually the families of curves as we vary k. So there are lots of curves collected here. And we're looking for, and then we picked the one point that is probably on here, a comma b, so that it's defined, such that that curve passed through that given point, and this curve happened to be the perpendicular to all the curves that are appearing here. So that is our orthogonal trajectory problem, but here's a different problem. This is a differential equation, so forget about the shape of the coefficient of dx part and coefficient of dy part. And this differential equation in differential form has an integrating factor. That's a statement, whether you can find it or not. Let's suppose that it has an integrating factor. And we'd like to show first these two things are equivalent. If we happen to have a curve, perpendicular orthogonal curve, then it'll give you an integrating factor of this differential form. And if you happen to have this differential equation, if it has an integrating factor, it means the existence of orthogonal family. This is a very algebraic problem, and this is a very geometric problem. You might find this problem very intuitive and simple and easy by looking at the picture and sketching it. But if I give you this problem and ask you to compute the integrating factor, algebraically, this is very, very puzzling, and often beginning students who just finished the Calc 3, for example, usually have very difficulty of seeing the existence of integrating factor, although intuitively many will believe that there is existence of this orthogonal curve. So it's an interesting connection. At the end, we're going to use something like this, where we're going to take this into an equation, and we will show that this one has a solution. What we mean by a solution to that one is a parametric solution. So there's a xt and yt such that it fit into this equation. Once we have that, we'll be able to show this correspond to orthogonal family. And once we establish these two things are the same problem, we'll be able to show that this particular equation has integrating factor. If you multiply something here and there, this will be an exact differential form. And at the end, and the surprising thing that we're going to do is that if you have an arbitrary differential form, m dx and n dy, and if it has an integrating factor, it all rises from this shape, namely it all rises from existence of an orthogonal family. So I wanted to write it up here clearly. At the end, we're going to show if you have just an arbitrary differential form that happen to have an integrating factor, then it is coming from the orthogonal trajectory. There is this curve and geometry problem that is tied to this one. So it is equivalent problem. That's what we're going to establish at the end of the video. So back to our normal slides. First, we're going to look at this situation where we have this orthogonal curve perpendicular to all this curve. Then we're going to show this equation, differential form, must have an integrating factor. So 1 implies 2. So here's a statement. We have a curve given by this Cartesian equation such that it's orthogonal to everything. By differentiating left-hand side with the parametric equation and using the chain rule, we get this one, gx dx plus gy dy equal to 0. And we assume that this curve, this one here, is perpendicular to all the level curves given by this f of x equals k. So the perpendicularity gives you the perpendicularity between these gradient vectors of these two functions. Here g equals 0 and f equals k. They have this two that they must be perpendicular to each other. If these two-dimensional vectors are perpendicular to each other, it has to be the case that if you swap the xy component of the gradient vector of f and switch one of the sign, they must be pointing the same direction. So same direction means k, and these scalar is not fixed. So every time you have different points, there must be a different scalar. So that scalar is a function of x and y. So the x component of the gradient, gx, must be the k times fy. Y component, gy, must be the negative k times fx. Well, obviously, by definition, gx dx plus gy dy is exact, and if you replace this gx gy with what we have it over here, that is, of course, an exact, and you can cancel those k here and k there. That'll give you our statement fy dx minus fx dy equals 0 has an integrating factor k such that, of course, so that this one becomes an exact equation. So that proves that if we have an orthogonal family, this curve without k factor has an integrating factor. Now this will be a converse, so we start with this fy minus fx part that has an integrating factor I, and we show that there exists on a curve that is perpendicular to all the families of a curve ck, which is defined by this f of xy. Since it has an integrating factor, you multiply that integrating factor I, then this becomes exact. That means this coefficient part becomes a partial of x of some function, and this becomes a partial of y of the same function, which is written here. There exists this function g of xy such that this part and that part is realized the partial of x and y. Now what we have to show is this function, the graph g of g set equal to 0 or something else. This will be actually determined by that initial condition or the point that curve is passing through a comma b. But it could be this 0 or s is partials of the same. So I think this should be kind of s instead of 0. Sorry about the mistake. And f of xy, you have to show these two things are perpendicular to each other. Of course, that'll be done through calculating the dot product of the gradient of these two things. So spelled out the components of the gradient of these two vectors, which is gx, gy, fx, fy, and we will multiply these two components and add together. That's the dot product. So here it is. Gx and gy has this identity in terms of partials of f. So that's written here. Negative ifx is written there. So if you multiply these two components, you get I fy fx. Multiply that two component, negative I fx and fy. So these two things are the same quantity, except the the sign, so it has to be 0. So these two vectors are dotted to 0, so they are perpendicular to each other. That proves that they intersect and 90 degree everywhere. So I showed that with the picture here. So it doesn't matter what your S is, and any curve you set equal to that, it is going to intersect a 90 degree. In particular, if you set this S to be g of AB, then this curve passes through A comma B, because we chose that S to be this number. So we pass through that point and it will remain perpendicular all the time to CK. So let me come back to this slide again. So far we have established these two problems, equivalence of these two problems, and we're going to establish the existence of parametric solution, sorry about that, to this differential equation, which is going to naturally transform to existence of orthogonal curve, therefore establishing that this has an integrating factor. So let's show this differential equation as a parametric solution. So actually, to show this one has a solution, we're going to be using the big theorem, existence and uniqueness theorem. So I hate to use the big theorem, but it's a good example to tie this very concrete problem, and then you have an opportunity to appreciate these powerful theorem, existence and uniqueness. So instead of we're looking at this as an equation in functions of x and y with the independent variable t, locally we can probably look at y as a function of x or x as a function of y. So let us assume we're actually looking at this as a function of x, so that we can put this one into context of the existence and uniqueness theorem, which says if you look at y as a function of x, then the derivative of y with respect to x, which in this way is calculated as this quotient of these two partial, but we can look at it as a functions in terms of x and y. And the condition of an existence and uniqueness theorem requires that partials of this one with respect to y is continuous. So under that additional condition, which requires this second partials are continuous here. So with that powerful theorem, we can say there is a solution around x equals a, and we have a solution y equals hx. For example, instead of writing yx here, decided to use something else. It's indicating that we actually have a formula here. But you can always rewrite this function in form of g of xy equals 0, namely y minus hx will be this g of xy equals 0. So let's put that into this context, that we found a solution, we put it into this form, g of xy equals 0 in particular, and we also have a parameterization, for example, x equals t, y equals y of x, yt. And that way it's a trivial parameterization, but let us put into this general context. So in particular, we have this way of representing the solution. So let me remind you of our problem. We want to show this differential equation has an integrating factor. And we just found a solution to this problem. So I am differentiating this equation with respect to t, and we get this by chain rule gxx prime and gyy prime, which is derivative of that, equal to 0. That gives us that this gradient g is normal to the velocity vector of this curve here. Then I'm going to juxtapose this, what we have over there. This is our original equation, fyx prime minus fxy prime equal to 0. That was a dx and dy. So that means this fy, that's not gradient of f, and it's a twisted gradient. So let me go ahead and fix it. So instead of that gradient, we need to have fy and negative fx in that place in here. Okay, now I fixed it. Instead of the gradient of f, this is kind of switched around and with a different sign. So I called it as just a twisted tilde symbol, gradient f twisted like this. So if you look at these two things, these two vectors are both perpendicular to the same vector. So that puts in a situation to conclude that these two vectors are scalar multiple to each other. So they're kind of parallel or completely opposite. So you can equate it that this gradient of g is a scalar multiple of a twisted gradient of f, where k depends on depending upon your base point x comma y. So this is a function of x and y. So if you look at it here, this fy and then negative fx, when you multiply k both sides here, that becomes a gradient of x and gradient of y of the same function. That's exactly the meaning of having an integrating factor. So here I'm showing that three statements again. So we prove that this basically is the existence and uniqueness theorem, that we know it has this differential equation here has a solution, and we show that it actually forces this one has an integrating factor. This which really went through this perpendicular orthogonal trajectory problem. So not only these two are equivalent, this one always has an integrating factor, and that's always tied up to the orthogonal trajectory problem. Now let's look at this interesting question. Do all the differential formed with the integrating factor rise from this particular one? What we have just discussed is that if you have this differential form, in particular this coefficient have this strong relationship like this, then we know it has an integrating factor because of the existence and uniqueness theorem. That's what we just did. But do all the differential forms have integrating factor? Are there in this form? That's basically our question. So computing integrating, thinking about the existence of integrating factor, now if answer to this question is yes, that makes this problem of orthogonal trajectory, namely the existence of this family orthogonal trajectory problem, it is equivalent to now the existence of integrating factor of m dx and n dy. So let's start like this. We have this differential form, and it has an integrating factor ixy. So this means that if you multiply I and both of the component, it becomes a partials of x and y, partial x and y of the same function gxy. And this is a key thing. Well, we're not looking at gx dx and gy dy. We look at actually a twisted one, gy dx minus gx dy equal to 0. And because of the existence and uniqueness theorem, we know this one has an integrating factor. So I call the integrating factor k. So if you multiply kk here, this becomes exact. Exact means there is this function f I call. So fx is k times gy, fy is negative k times gx. Now if you rewrite what this gy and gx are, gx was gy here was in, so that replaced by this in. This fy negative k times gx, that gx is replaced by im. So fx and fy now is in this form. So I guess we're already seeing the shape, and we want to divide both sides by ki, but when you divide it, you want to make sure that it's non-zero. So that's why we need this assumption. Gx, let me show you what gx was. Here the gxy is the function such that this turns to an exact after you multiply the integrating factor I. That's the function g. So we assume the solution to that problem has nice property such that the gradient is nowhere 0. This is also called the non-singularity of this curve. For example, the curve does not have a cusp, it's a sharp turn or self-crossing. If we have that kind of nice property, then it guarantees that the gradient is never 0 anywhere. So we assume that kind of thing so that this I will never 0. If I is 0, then you can see gx and gy is 0. That makes the gradient vector at both components 0. So if we have that property, then we know this integrating factors never vanishes completely. And here, gy and gx, they're never at the same time 0. Therefore, I think we should be a little bit careful with the k part here. Having more information about this integrating factor k, you have to go back to the existence and uniqueness theorem of how we solve this one and conclude that this k is locally never vanishing. But I have not prepared that part in here, so we can simply assume that k part is non-zero as well. Once we have that, and I and k, these are non-zero integrating factor. Therefore, we can write this m and n into this form here. Okay? So this explains, except that non-zero property of this k part here, this quite explains that the problem of having a integrating factor of this differential form is equivalent to having this differential equations for some two-variable function of x, and this is exactly the orthogonal trajectory problem. So integrating factor and orthogonal trajectory problem is equivalent. So all the differential equation with the integrating factor arises really from this shape, arises from the orthogonal trajectory problem. So let me add this last word about the part I was sloppy about this non-zero integrating factor k part. I think it's kind of complementary if you can assume that existence of this curve g, which everywhere the non-vanishing gradient, which is the non-singular condition everywhere, it's just smooth and there's no self-intersection or cusp part, then we can find the orthogonal family in such a way that they have the same property that the gradient, because it's kind of complementary to each other, the gradient will not be vanishing. For example, if you find a curve like that, and if you take them to a squared or a third power, it'll easily create an example. The gradient vanishes because of the multiplicity, but we can always choose a nice one such that the gradient is not equal to 0 and is orthogonal to each other. So assuming this one never equal to 0 gives us a choice that we can choose f of xy such that the gradient vector is never equal to 0. Therefore, this k must be non-vanishing everywhere locally. So therefore, the k and I are never 0 locally, and so that we could conclude the rest of the part. Thank you.